Welcome to week 6 of Mathematical Methods for Quantitative Finance. We're going to continue this week talking about linear algebra. Last week we got the basics down, vectors, matrices, and some of the arithmetic rules for working with vectors and matrices. And now we're going to look a little bit deeper into factorizations of matrices and the types of problems you can solve with them. So this week's menu, I'll start off with a few more properties or types of matrices. So there's a transpose is an operation you can do on a matrix, and a permutation is another operation you can do on a matrix. And then I'll talk a little bit about vector spaces and subspaces. And then I really want to get into sort of the meat of this week's lectures, which are going to be operations. So when you want to do something to a data set, often that something can be written down as a matrix, and then I can complete that operation just by doing matrix multiplication or some potentially more complicated formula involving matrix manipulations. And the example I'm going to use to show how that can be done is a variance-covariance matrix, which in section 4 I just start calling covariance matrix because the full name is kind of difficult to pronounce. Then in lecture 5, I'm going to introduce yet another type of matrix called an orthogonal matrix. And this is a matrix that has a very nice property that its inverse is also its transpose. And then I'm going to look at some factorizations of matrices that basically involve factoring the full matrix into orthogonal matrices and then one more matrix that has some sort of special property. So in the singular value factorization, I'm going to end up with two orthogonal matrices. So these are very easy matrices to work with because they have this nice property that their inverse is equal to their transpose. And then the third matrix is going to be a diagonal matrix, which that means that if I look down the main diagonal of the matrix, those elements are non-zero, but any other element has to be 0. And so again, this is a very easy matrix to work with because its inverse is just the reciprocal of each one of those diagonal elements. And then I'm going to use the singular value factorization to motivate something called eigenvalues and eigenvectors. And then finally, in section 8, I'm going to look at solving something called a least squares problem. And so this is if I have a scatter plot of values, so I have x values on the x-axis, y values on the y-axis, and then I want to put a best fit line onto that plot. The slope and the y-intercept of that best fit line you calculate by solving a least squares problem. And so I'm going to go over how you can use a matrix factorization called a QR factorization to solve that problem.